Welcome to section 4.4. It's a big section, so let's just jump right in with the definition of a coordinate vector. Suppose you have a basis for a vector space. You can write every vector in the vector space as a linear combination of those basis vectors. That's because the basis vectors span the vector space. In addition, you can do that only one way, and the proof of that fact is down here below, and I'll just let you read that on your own. But the coordinate vector is simply the vector of coefficients. So you pluck off the coefficients of that linear combination, put them into a vector, and we call that the coordinate vector of x relative to the basis b. And the coordinate mapping is the map that takes a vector to its coordinate vector. So let's look at some examples. Find the coordinate vector of this polynomial in P2 relative to the standard basis, 1t and t squared. Now, note that that has three basis vectors in it, and so our coordinate vector is going to be in R3. So what we do is we write P as a linear combination of the standard basis vectors. So that would be 2 times the vector 1 plus 3 times the vector t plus -1 times the vector t squared. So P bracket sub b is the vector in R3. Plop off the coefficients, 2, 3, -1. Okay, let's do another one. Find the coordinate vector of -5, 2 relative to the standard basis of R2. Now, the standard basis of R2 has two elements in it, and so we're going to get a vector in R2. So let's write -5, 2 as a linear combination of E1 and E2. So that's -5 E1 plus 2 E2. So XB is equal to the coefficients -5, 2. Note, in this case, xb is equal to x. So in this case, when we take the coordinate vector, we end up with the vector we started with. All right, find the coordinate vector of this matrix 1, 2, 3, 4 relative to the standard basis of M2, 2. So we need to write 1, 2, 3, 4 as a linear combination of B1, B2, B3, and B4. All right, well, that's pretty easy. Take 1 times B1 and 2 times B2, 3 times B3, and finally 4 times B4, and that does it. X sub b is the vector in R4, 1, 2, 3, 4. So I get vector in R4 because the standard basis of M2, 2 has 4 vectors in it. All right, and I hope you can see the pattern there. In general, if x is A, B, C, D, then x sub b, just replace 1, 2, 3, 4 with A, B, C, D, XB would be A, B, C, D. Okay, now let's go in the other direction. Suppose we're given that the coordinate vector is this, and we're given a basis, and we want to find x. Well, if I call this B1, this B2, B3, and B4, when I'm told that the coordinate vector is 1, 2, 3, 0, that's telling me that x is equal to 1 B1 plus 2 B2 plus 3 B3 plus 0 B4. So that's 1, 0, 0, 0 plus 2, 1, 1, 0, 0 plus 3, 0, -1, 1, 1 plus 0 times 0, 0, 0, 1. And you can check that's 3, -1, 3, 3. All right, we want to be able to go back and forth between a vector and its coordinate vector, and we've already seen how to do that in one case. Let's do it again with vectors in R3. So I'm given a basis here of R3, B1, B2, B3, and I'm given XB, and I want to find x. So that's very similar to what we did above. X is simply twice B1, which is 1, 0, 0, plus 1 times B2, which is 2, 1, 0, minus, well, plus -1 times B3. And if you add those vectors up, you get 3, 2, -1. Okay, the harder direction, you're given a basis, which we have above, that's the same basis, given x, and we want to find xb. So what we want is the coefficients in this equation right here. And so let's reduce the augmented matrix, and I already did that just to save time. And imagine there's a dotted line there, so my coefficients are -2, 0, and 5. So XB is -2, 0, and 5. Now you can do a safety check. You can check, is it really true that x is -2 times B1 plus 0 times B2 plus 5 times B3. And if you do the arithmetic, you will see, yes, it is true. All right, why don't you pause the video and you try this one. both directions. Okay, hopefully you did that. Easy direction. X is 2b1 plus 10b2, and that turns out to be 216. All right, this direction, we want to solve c1b1 plus c2b2 equals x. So we want to reduce the augmented matrix, put b1 in as the first column, b2 in as the second column, augment with 210, and that just takes one row operation. We get 0, 1, 4 here, so x sub b is 2, 4. All right, so here's where we're really going with this. If you pick a basis for a vector space V, then the coordinate mapping is an isomorphism from the vector space to Rn. Now, an isomorphism is a one-to-one onto map. And what that tells us is that anything that's true about a set of vectors in the vector space V is also true about their coordinate vectors in Rn. Now that's really handy because it's very easy to work in Rn, and sometimes it's not so easy to work in the given vector space. So here's an example. P2 is isomorphic to R3, and the isomorphism is you take a polynomial a plus bt plus c t squared, and it gets mapped to its coordinate vector abc. Because really, if you have a quadratic polynomial, the only thing that's important to know is the coefficients. Another isomorphism is the complex numbers are isomorphic to R2, and the isomorphism would be you take a complex number, a plus bi, and you map it to the vector ab. Okay, let's look at another one having to do with polynomials. I've got a set here of 4 polynomials in P2. I'm going to write down their coordinate vectors. So for the first coordinate vector, I just want the coefficients of 1 t and t squared in that polynomial. So that's 1, 1, and then 0 because there are no t squareds. Okay, for the second guy, I want 2, 1, 0. Third guy, I want the coefficients of 1 t and t squared in that polynomial, that's 0, 1, 0. And then the fourth guy is 3, 4, 1. All right, and we're going to answer some questions about these polynomials by looking at their coordinate vectors in R3. So the first task I've already done. I put the 4 coordinate vectors into a matrix and I reduced to echelon because I want to look for pivots. Got a pivot here, a pivot here, and a pivot here. So question 3, determine if the polynomials span P2 by determining whether their coordinate vectors span R3. Well, their coordinate vectors do span R3 because I have a pivot in every row of that matrix. All right, and then are the polynomials linearly independent? No, they're not, because I don't have a pivot in every column. And so finally, based on questions 3 and 4, do those 4 polynomials form a basis for P2? No, they don't. They span, but they're not linearly independent. And so for a basis, you need both. And we're going to use this notion of isomorphism next time when we talk about dimension. And that is the end of this section.